Basically, when we look at the world, we see particles, we see energy. However, when we do not look at the world, when something is not interacting with the world is not a bunch of particles, it's not a bunch of things, it's a bunch of waves, it's a bunch of undulations in some medium yet unknown. And so when you want to model quantum processes, you have to understand wave dynamics. So the first thing I'm going to talk about wave dynamics and how you model waves in graphs, how you model energies that are oscillating. And once we understand that, we'll understand how to do an actual quantum form. So we'll start very simple. Wave dynamics in graphs. Let's just do a little visualization. Here. You can start off with a little gremlin. He's going to bounce. How would you model this? Well, a graph, there is no space outside the graph. The topology of the graph is space in and of itself. So when you want to say that the vertices are undulating, where are they undulating in? There is nothing beyond the graph. So how do you model something like an oscillating vertex, a vertex in which energy is going up and energy is going down, some amplitude around some space energy state. And so the way to do that is to understand how energy is flowing through that vertex over time. So over time, how much energy does a particular vertex have? The problem is traversers, the things in which move energy or propagate across the graph, are indivisible objects. There are states. So you say, okay, well, there's a traverser, but it's an object. How do I make it indivisible? How do I piece it apart and fuse it to a graph so I can represent energy at different values, not always just 1.0. Moreover, how do I represent negative amplitude, a negative 1.0 energy? So when you have something going up, that's a plus 1, that's a negative 1. So how do I do that? And so in Tinkerpop 3, Gremlin introduced the concept of a stack. So while the traverser itself might not be divisible, he carries a little sack with him. And this little sack is like a bag, and he has an object. And that object can be anything. And so for our simulation in this initial part of the talk, we'll be talking about him carrying a double floating point. So let's not worry about the algorithm. Let's just go ahead and show how this looks. So we have a gremlin with a 1.0 energy stack sitting at this particular vertex. And so I have this little dot graph schematic kind of just showing you initially what this wave will look like. Again, that doesn't exist how to visualize. So the next step, the energy can split like this. Half of it goes one way, half of it goes the other way. Realize that the total energy in the graph is still 1.0. Meaning the total amplitude. We have not lost any energy to friction. We conserve energy throughout the system. And we can split it again. And notice that when we split it, 0.25 energy goes right, 0.25 energy goes left. However, 0.25 went right, 0.25 went left, and 0.25 went right. So we have some constructive interference in the sense that we have a 0.5 now in the middle. So we can keep doing this and propagating numbers like this. And now we have this notion of energy using a graph. Now let's go ahead and do how is this algorithm implemented in Gremlin. It's quite simple. We say I have a graph G, and I'm going to create a gremlin with a sack. And his sack is going to have 1.0 in it. And anytime two sacks interfere with each other, whenever two gremlins merge with each other, their sacks are going to sum together. And I'm going to start this gremlin off on vertex 3. So I create a gremlin, vertex 3, and he has a sack of 1.0. And now for 3 times, I'm going to repeat this process 3 times. I'm going to go ahead and create 2 splits. One split is going to go left, and one split is going to go right. However, the guy who goes left, his sack is multiplied by negative 0.5, and the guy who goes right, his sack is multiplied by 0.5. Have we done it more than 3 times? No. So we repeat the process again. So now those guys split again. And again, we get the constructive interference in the middle. So the end traversers have 0.25, 0.25, and the guy in the middle has 0.5. Here's the mathematics to kind of get that. You can see how these numbers sum up. 2 times. Do it again. Then you keep repeating this process. So we can see that we're using energy over a particular graph. So what is our space? Again, our space is the graph, and what we're trying to model is a wave of energy, vertices going up and down, some kind of like frequency over time, and so we diffuse an energy. Because traversers are indivisible objects, we need to model the energy as being contained within the traverser with the notion of their sacks. When traversers split, meaning that when they have two options, they can go one way or the other way, they will split and they'll split that energy accordingly and make sure that they preserve the total energy from where they're split. When two traversers merge, or multiple traversers merge, their energy is summed together. When the two energy stacks that are summed together have a parity that's the same, meaning both negative or both positive, you're going to get constructive interference. Meaning you're going to get a whoop. And if you have negative interference, when a negative and a positive hit each other, so if a negative and a positive hit, they just go to zero. So you get destructive interference. So this is kind of just principles of how waves work. You're just moving energy through some kind of medium. This medium is the graph, and you have constructive and destructive interference. Okay, so that's a very simple explanation of what's going on. Let's kind of move it up a notch. And let me explain quantum mechanics in terms of the Copenhagen interpretation. So there's multiple interpretations of quantum mechanics, primarily because no one understands what's happening in between analyses of the system. So a system can be set up, and then as long as nothing's disturbing that system, something happens. The moment we disturb it by looking at it, it goes back to being a particle kind of system. And so no one knows what happens during this stage when no one's looking at the system. And so because of that, there's been multiple interpretations of what's going on. The most popular is the Copenhagen interpretation, of perhaps the first interpretation of what was going on. You might hear words like a wave function collapse. You might hear like consciousness comes in and kind of affects it in some way. There's other interpretations, such as the multi-world interpretation, that the universe just keeps splitting, and there's just millions of unlimited amount of versions of us. Every time there's a decision we make in our life, one version goes this way, one version goes that way. There's a pilot wave theory of Bohm, which basically says everything in the world has a pilot wave that associates with it. So while it might look like an object, I'm actually undulating and I'm moving in a medium. So there's various interpretations. Let me just go ahead and explain the Copenhagen interpretation, because that is actually how the semantics of the Copenhagen interpretation map very nicely to how Gremlin has a reversal machine executes. So here's take this little toy graph. 6 vertices connected as such. Now let's take our traversor, our particle, be a little gremlin. And so gremlin, you can do G dot means 0. It basically says I want to put a particular gremlin at vertex 0. And then I can say dot out, meaning take one step out. When I take one step out, the gremlin now is at vertex 0, is now at vertex 1. Here is where the function stuff happens. What do I do when I do a dot out again? Now the gremlin has choices. He can either go to 2 or he can go to 3. What does he do? He goes, yeah. When there's a fork in the road, he takes it. And so in computing, there are 2 legal paths, so both paths are taken. And this is what we see every time gremlins and gremlins have to make a decision. They make both decisions. They just split. So you get a clone of the object in essence. In physics, if we were to do this, this would violate the conservation of energy, meaning we created 2 particles from 1 particle. And this is not allowed. We created matter out of nothing. And then we can go out again in graph computing. We say, yeah, there's 2 length 3 paths that lead to vertex 4. And in physics, this would be like, well, now you have 2 twin particles that are coexisting at vertex 4. This makes no sense. And then for vertex 5, argument. So let's talk about physics. What happens when a physical particle is faced with a choice? So if you have a particle at this particular point in space, and it can go either 2 or 3, what will it do? Interestingly enough, it does take both options. You say, well, that violates the concept of conservation of energy. This indivisible particle divides, and it actually doesn't become a particle at this point, it becomes a wave. And so while we can't see that there are 2 particles, one at vertex 2 and one at vertex 3, the moment we go to look to say, hey, where are you, particle? We get something called a wave function collapse, meaning that we only see the particle either at vertex 2 or vertex 3. And then you may ask, well, if you only see it at vertex 2 or vertex 3, why do you even say it took 2 paths? It obviously just took 1. Randomly it took 2 or randomly it took 3. And the reason we know that it actually took both paths is because of something called wave interference. And so we can infer that actually both paths were taken, even though every time we look at the system, only 1 path is ever seen. And this is the kookiness of quantum mechanics. And what's interesting about this is, what do I mean by a particle? And so particles, when we see quantum behavior, we typically see these photons, we see these electrons. However, there's a group of scientists are becoming more adept at putting things in what we call superposition, turning things into waves. They're actually becoming better and better at making sure the system doesn't decohere, meaning the system doesn't observe, it doesn't get friction from the environment, it doesn't interact with the environment, to the point where they're starting to put bacteria into superposition, where a piece of bacteria can take multiple paths, multiple options. So we're starting to see that as long as something doesn't interfere with the system, if it's kept in its own void, it starts to, it goes into multiple directions. It takes all options. And so prior to observation, we first start off with the system, we see a particle, we see a thing. Prior to observing it, it turns into a wave, and then when we go to observe it, it comes back into a particle. And again, there's other interpretations of quantum mechanics, and we'll splatter them throughout the talk. So the most important concept in quantum mechanics now is, yes, okay, this particle can go both ways. And we say, well, how do we know it went both ways? Well, because this concept of a wave function. So what is the quantum wave function? What we see is that when you start a system off, I'm going to take an electron or proton and put it at a certain point in space. It is a thing. It exists. It's unique. The moment I stop looking at it, or nothing's interfering with it, it goes into a superposition, and it becomes a wave. And then when I go to look at where it is, I shine light on it, it collapses back to an individual particle. And so we can actually observe the first state of a particle, which is preserve the end state of the particle. However, we infer that these things are happening, that there is a superposition, that there is a quantum wave going on. So let us do a true quantum walk. And this has been done in the lab many times with particles, where we can simulate it with graphs, and we can simulate it with a gremlin quite easily, actually. So let's take a 101 vertex line graph. So this is the graph that keeps going on to vertex 101, or to 100 and then to 0 on the other side. And the center of the vertex is the vertex 50. Now, we're going to put a little gremlin here. And this gremlin sac now is a vector. It has a 1, 0 in this vector array. And what we're saying is it has a definite location right now. This particular gremlin is at a particular space. And now it has this thing called potential, or a spin, or a trajectory, or an emphasis towards. And we're saying that it wants to go left. It has this tendency to go left. It's spinning in a certain direction. And that's projecting it towards the left part of the graph as opposed to the right part of the graph. In the article, we call this traversal superposition as opposed to spin. It makes more sense when you think of the gremlin at a particular branch of the traversal. Is on the left branch or is on the right branch of the traversal. In physics, they call it spin. And so you can say, okay, at this particular moment, time frame 0, where is the gremlin? Or where is the particle? And the way to figure this out is basically to figure out how much energy is at any one wave. And it's actually the square of the total energy at the particular point of this vertex. So 1 squared plus 0 squared equals 1 squared. So the probability of seeing the particle at vertex 50 at this point in time is 100%. But now let's act like we don't want to see it. What happens next? The gremlin goes into a superposition. And so there is these operators, and they're called unitary operators. And a unitary operator guarantees that the total energy in the system is always conserved. And so if I multiply this 1, 0 vector by this particular matrix right here, this H matrix called a Hadamard matrix, I'm going to get a vector that's 1 over square root 3 over 1 over square root 2. So in essence, even though the particle is tending to go left, you can also go right. So part of them is going to go right, part of them is going to go left, while still conserving the total probability of the system. Left particles going left and right will keep their sign. Right particles that go right will flip their sign, according to this particular operator. There's multiple types of operators. Keep it very simple. This is 1 and -1. This is the only unitary operator that works in this operation. It's not a complex number. It's a real value number using ones and negatives. So keep the math very simple. And so the math works out like this. When you multiply this vector, this 1 over square root of 2. Bear with me. Now this vector looks like this. It's called point set. We have inverted, we have put the gremlin into a superposition, and now he shifts based on that superposition. So the left aspect of him goes left, and the right aspect of him goes right. So we can see we projected out the left component, and now it's 1 over square root of 2, 0, and the right component 0, 1 over square root of 2. And then you can say, okay, what is the probability that I'm going to see this particular, where are we going to see the particle if I was to look at it, shine light on it, and work out the math. 1 over square root of 2 squared is 0.5, likewise. And so if we look at the plot, what is the probability of us seeing it at vertex 49 or 51? It's both 50%. 50% chance that we're going to see the particle there. We do it again. We do another a shift step. We get now constructive interference here. So the potential going left and the potential going right is now going to merge back onto that vertex 50. I run the probabilities, and now you can see that we have a peak now at vertex 50. Do it again. And now we get some deconstructive interference. Deconstructive interference happens over here because of the negative sign. Everything spinning right tends to go negative. So when it superimposes on itself at 51, we have a cancellation. And we look at the probability here. And so we can just keep running the simulation, and we can see the probability of where we're going to find this particular gremlin. And so let's go ahead and fast forward to iteration 50. In iteration 50, this is what the probability distribution looks like. So the wave function is some undulation of negatives and positives in this vector plane, but when I square those numbers, I can turn it back into a probability distribution. So here's our probability distribution of where the particular particle is going to be. And so when I shine light, when I perturb this system with light, what happens? In essence, I sample this distribution. This is where quantum physics leads us. We know that there's a probability distribution because every time we sample, we just build up that probability distribution. So we know that there's going to be a high probability we're going to see the gremlin or the traversor or the particle at vertex number 16. Everything collapses. And when it collapses, now we have 100% probability we're going to see it there. Again, we went from a classical system to a wave system back to a classical system. Now we're back at 100%. We could have seen the gremlin at vertex 12. Again, this is a probability distribution. It's very unlikely we would see it here, but there is some probability there. So when we sample, there is a probability that we'll see the particle at that particular point. However, we would never see it at vertex 50 or 51 because there is actually no wave energy at that particular point in space. And so how do we model this with gremlin? It's quite simple. Here's the code right here. In essence, we're going to go ahead and create a gremlin with its SAC being 1, 0. So we create an array, 1, 0, that's our vector, that's our energy vector for this particular gremlin. And then we have the stack sum operator, which just is entry-wise addition. So whatever I'm adding, the first component and the second component just add together. And then I start the gremlin at vertex 50. So he starts in the center of the graph. And now I'm going to repeat this process 50 times. And so the first thing I do in this repetition is I'm going to Hadamard. So that's where I multiply the stack by this particular unitary operator. We'll talk about unitary operator in a bit more in a second. And then after that, I do a projection. So the stack moving left gets projected by this constant 1 times 0. So this is like a binary filter. The 1 times 1 over square root of 2 is 1, and 0 times 1 over square root of 2 is 0. So that's my left component. My right component is 0 times 1 over square root of 2 is 0, and 1 times 1 over square root of 2 is 1 over square root of 2. Repeat that process 50 times. I keep diffusing this vector over and over and over. And then, how do I create this probability distribution? So I'm going to shine light on this guy. And when I shine light on this guy, what do? I got to norm the vector. I got to do the squares of the probabilities of the amplitude at that particular vector, and I create this probability distribution. And then from that probability distribution, I sample 1 where it's biased by the value of that distribution. So, in essence, I have walked a traversor, a particle, on a line of space. And that is, in essence, quantum mechanics. And what any kind of simulation of quantum mechanics with a single particle is going to yield you is what happens in the lab. Now, we were using unbalanced, this thing called a Hadamard operator, which is an unbalanced coin, which tends to bias things towards the left. There's a balanced unitary operator. It uses complex numbers, which rotate things in space a little bit differently, but we won't concern ourselves with there. What's really important, though, is unitary operators. So a unitary operator conserves the total energy in the system. why there's this wave function, and why things turn into waves, because there's nothing that disturbs it. What is disturbing something? That's friction. Once this wave energy hits a wall and smears against the wall, and energy is put into the wall, at that point the thing becomes a particle. So as long as I maintain total energy in the system is always 1.0 and nothing's going to perturb it, it'll be this wave. So that's very important to understanding how a quantum system works, and you cannot have friction. And it's possible to reverse the operation. What is friction? When I put energy into something else, that something else now takes that energy, and that system has lost information. And so quantum mechanics is all about no information loss. And in fact, quantum computing, quantum gates are reversible gates. No heat is lost. If you have a quantum chip, there is no heat generated from that chip. Because once you generate heat, you've lost information. Once you've lost information, you cause decoherence. Once you cause decoherence, the wave functions collapse. You're no longer quantum computing. So all quantum operators are equilibrium operators, meaning they conserve energy they have to, or else you're going to collapse that waveform. And it's so important to not collapse that waveform because you get this parallel computation. All those little gremlins. One particle is diffused, and now I can hit the parallel operations. So in matrix notation, if I say I have a unitary operator and I multiply by its conjugate transpose, think of it as transpose, this is the reverse of the operation, I get the identity. And that's the whole point. You have to make sure that you can reverse this stuff and you always conserve that energy. This is what is really cool. So if I was to do a classic random walk on this line, starting at vertex 50. So a classic random walk is I got a traversal at vertex 50. You can go randomly left or you can go randomly right. You go, okay, I'll go left. And you go, okay, I'll go left again. You go, okay, I'll go right. Now I go left. And then I go left. And I go right. And I go left. And he does this for 50 steps, 50 steps. The probability of where you're going to see him is this right here, where on the variance of that distribution is 7.07. Meaning you're going to see that classical traversor within 7 steps of vertex 50. So a classic random walk on a line is typically going to be around vertex 50. With the unitary, with quantum mechanics, which is really nice, is that when you do that same one random walk, and we're using our y operator now to a balanced distribution, look at where you're probably going to see that particular walker. So a random walk, a quantum random walk is going to explore more of the graph. And the reason it does this is because of interference. The moment that there is a lot of activity right here, it starts to cancel itself out. And because of the unitary operator, I have to conserve that energy. The moment that the probability drops right here, it has to go up somewhere else. So it tends towards novelty. It tends towards places that it hasn't seen. Because once it starts to reverberate in places that it's seen, that probability starts to get pushed down, and because the unitary operator, you can't lose friction, you can't have friction, you can't lose information, that probability needs to go up somewhere else, and it's going to go up on the sides. So you can walk a lot further with a quantum walk versus a classical random walk. Now, we're going to do a simulation that I'm sure this is kind of, most of you have seen this in some sense. This is what started quantum physics when they started realizing how does light work? What happens when light is shot out as a continuous stream versus light shot out as a photon? So Thomas Young did this famous experiment in 1700 time period, and it looks like this. He wanted to know whether light was a wave or a particle. And so he created a simple experiment where you have this kind of film right here that can detect light. It'll get brighter or darker. This dark gets brighter and light hits it. And then he created this screen. So if light hits here, it's going to get absorbed by the slits. Or light can only go through these particular slits. The walls don't allow it to go through. And then he has a continuous light source, this being a candle. So he's going to say, okay, I'm going to put this candle here. I've got this slits right here. What is the pattern that's going to look like on this particular film? His hypothesis is that he believes it was going to be a wave. And he goes, well, if light's a wave, what's going to happen is there's going to be constructive and deconstructive interference. So this energy is going to propagate out, it's going to produce through slits, and then emanate from those slits. And where the emanation from those slits touch each other, you're going to get some kind of interference pattern. And if it hits at the right spot, you'll constructive interference. And And so he thought he could get some peaks like this. And in fact, he did get these kind of peaks. He saw refraction patterns similar to water waves. So he goes, oh my god, it's just like water. And this is what the concept of heat is around. So, okay, so we know that energy propagates through some kind of a medium. We know that sound goes through air. We know that waves go through water. So what is light going through? So there must be something that we don't know called the ether. And this is what's vibrating when light is being shined through it. And so it wasn't until, I don't know, early 1900s, and I guess started quantum mechanics was like very much like 1915, 1920 kind of season. And they have been able to control light a lot better. We don't need to have a candle. I can emit one photon of light, the most minuscule amount of light that's possible before you even consider anything else. It's like the limit of what amount of energy I can possibly release and still have it be light. So he goes, okay, well, I'm going to do the exact same experiment, but now my source is just going to emit one little particle as opposed to a continuous stream. And he's asking himself, okay, now what is this film going to look like? And he says, okay, well, I believe since I'm shooting bullets, in essence, I'm shooting those particles, that what the interference pattern or the pattern on the screen is going to look like is that there's going to be a 50% chance it goes to the left slit and a 50% chance it goes to the right slit. And most of my energy is always going to build up here in the long run behavior. I'm going to get these two little humps, just like shooting a gun with a slit is just going to get directly on the slits. So we ran the experiment. Okay, shoot photon 1. Pop that right there. Let's shoot photon 2. Pop that. 3, 4. Let's go ahead and fast forward. At photon 20, he's like, wait a second, there's something weird going on. I'm actually getting the same interference pattern in the long run. And so what he assumed was that when I shoot an individual photon, it has to take both paths. It's splitting itself, it's becoming a wave, diffusing through both slits, and then when it hits the screen, it localizes itself based upon that probability distribution generated by the wave function. So this is where they said, oh my god, this is a whole new phenomenon. There's no such thing as particles. Particles only exist because we interfere with them. The moment we're not interfering with them, they're going in every potential direction. And that's where we get the multi-role interpretation. So the role keeps splitting. And when a particle goes left and a particle goes right, there's one role where a particle goes right, and there's one role where a particle goes left. And the Bohm interpretation of quantum mechanics is called the pilot wave theory. And in essence, a particle has a little wave that goes around it. So while he might be going down here, his wave energy is going down here and might push him in one particular direction. And there's problems with the Bohm theory with the entanglement that they can't solve yet. So while it looks really nice, you say, okay, fine, there's a particle, there's a wave around it, and while the particle is being bounced towards one direction, this wave energy is going to come around to the other slit and affect it. And it's very nice for single particles, multiple particles. There's no good explanation for how entanglement works. And that's another thing we're talking about. And so, in Gremlin, this is very simple to do. You can say, okay, well, I want to do the exact same experiment, so let's go ahead and create a lattice. Don't worry about the colors. The colors mean nothing. I just want to highlight certain points. This particular vertex, we're going to start our Gremlin out. Notice that our slits, what our slit is basically a cut of the lattice. We just cut out the edges right here. And we leave the edges here, cut the edges out there. So now we have two slits. And then our photoelectric film on top, you know, it's going to be registering where the wave function collapses, is going to be on top. And so we're going to do something along the lines of this. We're going to use energy distribution. And then all of a sudden collapse it back to a single particle. And then the answer that we're going to get is going to look like this. And this is actually what Gremlin gives us when we do traversal. So it's a pretty nasty looking traversal, but it's actually very self-similar. There's a pattern to it, so bear with me. There's 4 degrees of freedom that the Gremlin can do. You can go left, you can go down, you can go right, or you can go up the lattice. So he's got 4 options. And so his energy vector of how he's going to superimpose himself, or how much of him is going to go left, right, up, and down, is now represented by a 4 vector. And we're going to say the third component, the one he's tending to go up right now. And again, when two vectors, when two stacks hit each other, they're going to sum, entry-wise sum. Very simple. And we are going to start on vertex 10. So that's our single photon of light down at vertex 10. And now we're going to repeat. And so the superposition, the unitary operator we use is called a Grover coin. If you multiply R by R transpose, you get the identity. And what's really interesting about this coin, first of all, is it's just using normal numbers, not using complex numbers, it's easy to interpret. If you keep going, look at on the identity, the line on this thing called negative numbers. If you keep going in the same path, you're going to oscillate. You're going to 1, negative 1, 1, negative 1. So this reverses one like this. The moment you go in another direction, it keeps this sign. If you keep going on that same direction, then you go 1, negative 1, negative 1. So you just have these kind of oscillating gremlins going like this in all directions. And so we're going to diffuse the wave in 4 directions on this lattice. We can go left, right, up, and down. There's this component right here. This is I discussed in the article. Is how do you deal with walls? So this lattice is walls. I mean, there's on the walls and as well as the slits. What happens when the hook into the slit hits one of the barriers? So we need to reflect that energy. We cannot have any friction. We cannot have decoherence in the system. We've got to make sure that the wave energy is constantly conserved. And so I'm not going to discuss it here, but that in the article we discussed how you do these kinds of splits and how you reverberate energy in the system. And then as before, once we've done this 22 times, 21 or 22, 21 doesn't give us a nice splatter. We need one more step. So that's what I do. How we generate probability distribution and classical waveform by sampling. So this is a quantum walk on a bounded lattice, and this produces the same experimental result. Of course, there's variation from these different coins and where the light source was, and then all this experiment and whatnot. It produces the same results that we did in physics. And so if we look at step 22, you can see where the wave energy is in the system and how it's been diffused. Darker is less probability or less energy, and lighter is more. However, it's along the back vertices that we start to get back to where it's ultimately going to register and where the sampling is going to happen. And that's what probability distribution is. Okay, so what we've done is we can do quantum walk simulations on lines and graphs. There's various rules. We have to make sure that we don't have friction, we don't have decoherence, but as long as you conserve that wave energy, we know how to propagate a wave, we know how to undulate a wave through a system. However, we're doing a simulation. We're not doing quantum computing in the sense that we're not getting complicated. All those little gremlins, when I split, that's a new little object I got to deal with. It's a new little object I got to deal with. So every time I'm splitting, I'm using clock cycles. Quantum mechanics doesn't use clock cycles. It still thinks there's one thing there. So a quantum computer, while my simulations, I'm producing, potentially billions of little gremlins. In a quantum computer, it only thinks that there's one gremlin.